Hi, my name is Oscar Wahlberg. I'm a Director of Product Management here at Nexenta. Today I'm going to start talking about Nexenta Edge, which is really our scale-out object and block storage solution that we're announcing. I'm going to start the conversation, kind of show you the very, very high-level architecture on a whiteboard, and then I'm going to call up Robert Novak, who's one of the our senior architects and one of the brains behind the solution, to kind of do a more deep dive architectural discussion of what we do differently. Hopefully that will keep you guys entertained. So we talked about Nexenta Store, our scale-up block and file solution. Nexenta Edge is architecturally very, very different. It's not a scale-up solution, it's a scale-out solution. So instead of adding many JBODs behind a server, you essentially use direct attached disk in a x86 server. Now you can have a lot of direct attached disk in that server, or you can work with kind of upcoming technologies like the Seagate Kinetic, but I'm sure Robert will actually talk a bit more about what we can do as well. To scale out capacity and performance, you add more of these nodes. So traditional scale out. It's really designed to scale from a small number of nodes up to a very, very large number of nodes. So think of this as potentially, that's a rack, add another rack, etc., to add capacity. It's really, designed to scale into petabytes and many, many petabytes of storage.
It supports fiber channel as well as...
No, it does not. What we support, and I'll get to that right now, what we support is outgoing interfaces for incoming or outgoing interfaces. For block, we only support iSCSI right now. Mm-hmm. I do not see us doing fiber channel. But iSCSI we do support. For object, first generation is going to be S3 and Swift, which basically are the de facto standards in the object world today. There are a couple of other interfaces that are interesting in the long run, but those are the de facto.
Are you looking at CDMI at the moment?
We're looking at CDMI right now. That's on the long-term roadmap in that sense. If that picks up and starts driving hard, then that will get pulled in. But right now, when we go out and talk to customers, S3 and Swift is what's on the floor, what people are interested in, what the applications are running against, and that's kind of really the key thing here, right? So we scale this out by adding many of these, and we run these, the services, S3 or Swift or whatever, you can scale those so that you can run on either what you can say is, one main node, or you can run it on many of these storage nodes. Now, the key things, and I'm just going to tee up Robert here, I'm not actually going to go into the detail here, but what's really unique with our solution is that we do deduplication on all the data that comes into the store. It happens at the edge, hence the name, Nexenta Edge. So we do deduplication, and that not only dedupes the actual storage, but also the network bandwidth we use. We also use a lot of network bandwidth optimization in the communication between these nodes. And this is what allows us to scale to a really large number of nodes or storage devices.
Are you using erasure code across the nodes, or are you just replicating?
Right now, the first release, or the 1.0 release that we're about to come out with, we're in a beta phase right now, it does not use erasure encoding. That's on the roadmap. We're using replication to maintain availability. The 1.0 product is really the key target use cases we're going after is, archival type solutions where you can actually push a fair amount of performance into it but also OpenStack environments. So we integrate with Swift, so we can essentially replace Swift in an OpenStack environment. The iSCSI component is fully integrated into OpenStack Cinder, so you can put all your storage or your VM storage in this object storage. We integrate with Glance as well, so we can take image repositories, and we have a user interface that you can kind of show, or a dashboard that we provide into Horizon, which is the OpenStack management UI, so that we can provide statistics.
Do you have client support requirements or anything like that? It's just standardized SCSI as far as you're concerned.
Standardized iSCSI, standardized S3 and Swift.
I use that. It's
so the iSCSI, so do you chunk the volume in many different objects, or is a single object?
So it is a single object that in the back end is fed by smaller chunks.
Okay.
Robert can get into deeper detail into that if we want to, but essentially it's presented out as a single LUN. Right? That single LUN is then backed by storage for many nodes so that we can get performance and throughput.
Okay.
Make sense? Question as well.
No, it doesn't.
Okay.
Just while we're on the high level, this isn't competing with Nexenta Store, then?
That's a great question. I actually see these very much as complementary solutions. Nexenta Store is the file solution. We do not provide file from Nexenta Edge today. That might be in the future, but right now we do not.
But you provide block from Nexenta Store as well?
Yes, so there will be some overlap, I'm sure, at certain customers, but this is predominantly a scale-out solution that is intended to feed much larger quantities than Nexenta Store is.
Are you going to ramp down development on Nexenta Store?
Absolutely not. But we're continuing to feed development into Nexenta Store, and we see that as a very strong product going forward as well.
Okay.
Is it going to be licensed on a per terabyte basis? I mean,
I'll get back to lessons in a second.
Yeah. So is this going to be able to run on bare metal, on top of Zen, and on top of ESXi as well?
So right now, this is bare metal. Well, bare metal in the sense that we're actually releasing this as a software product. It runs on Linux, so that's a change. It will be a standardized Linux OS, so CentOS, RHEL, or Ubuntu, basically.
Okay, so not as a VSA.
It could potentially run as a VSA, but that's not the target right now.
Okay, and it's an absolutely shared nothing backend this time.
Absolutely correct. Licensing question first. So we're working on different licensing models. Yes, it will likely be a capacity-based price.
So I have two questions. One is about the duplication. Most of companies are encrypting data before sending the object to the object store. And it could be a problem for the duplication, so it could be ineffective. And the second is how you manage the duplication, because if you manage the duplication at the node level and not at in a global namespace at the backend, you can get
you won't see as much benefit out of deduplication, right? So you're actually hitting some really key points there. Our deduplication is actually completely distributed and global across the entire namespace, and that is an excellent segue to kind of call up Robert here. Come on, Robert. So Robert Novak is a senior director at Nexenta, director of architecture. He's one of the key brains behind kind of how our networking and deduplication architecture works. So with that, I'll hand the pens to you. Okay. I'll take a step back.
Red one back.
Oh, you want the red one? You want a green one too?
It works better.
Okay.
All right. My name's Robert Novak. I'm the Director of Systems Architecture at Nexenta. I've been there for a little over 2.5 years. I've spent almost that entire time working as one of the two primary architects behind the Nexenta Edge object storage. I'm going to try and explain in as much detail as you want to dive into how we've put this together. But we tried to do something that is completely different from all the object storage that you're familiar with. And with that as a basic premise, I'm also going to make a really outrageous claim. And that claim is that it's not only different, but we have good reason to believe that it's going to be extremely superior to what you've seen. So, how can I make that claim? First of all, we do the classic techniques of taking an object and splitting it into chunks. No big deal, everybody does that sort of thing. Unlike other object stores, when we create replication copies, everyone has the notion that you make replication copies based on what's the current replication count per bucket. We don't care about that. You can actually have a separate replication count for every single object in the object storage. So that one object may have a replication count of 5, another may have a replication count of 20, and the third may have a replication count of everything. So it's replicated on all servers available. We started out with some questions about how we handle deduplication. So let's start out with the basic process. I'm going to start with get first. So over here you have your happy client who has just asked for a copy of the biz plan. Because here in Silicon Valley, that's all we worry about is the biz plan. So you get that object. You send that request over to a service that is running on your object cluster. That service runs on a server, of course. What we consider as where things don't go on servers. Things go on storage devices. So objects and chunks are stored on storage devices. We have no underlying file system requirement. And the reason for that is that everything is built on top of key value storage, like the storage provided by kinetic drives from Seagate that provide that API out of the box. Seagate has provided a TCP/IP paradigm for that. We've chosen a different paradigm. We've chosen to use UDP, and that's going to cause a lot of raised eyebrows. We'll show you how we do it in a very efficient way. We didn't make the Coringo type of mistake where we're multicasting to the whole network at one time. So let's talk about the get. When you want to get the biz plan, what happens on the client machine is you take the tenant bucket, pardon my handwriting, biz plan name, and you take that name and you run that through a cryptographic hash. And that cryptographic hash algorithm will reduce that to a long 512 byte, I can't spell here, value, and my favorite hex value, of course, is dead beef as a hex number. So dead beef is the cryptographic hash of that name. Now we want to find out where to find that. So we send across dead beef over to here. Actually, it can be done on this side either. It can be done either on a client library or it can be done on a broker that's on the network. This interface here is most likely an IPv4 interface because that's what most data centers have. What we use internal to the cluster is IPv6 on a VLAN because we want to isolate our network paradigm from the rest of the network. It is not visible outside to outside use. And all these addresses are internal only, and they're all mapped by gateways into that space. So we take that dead beef, and let's say we just take the bottom bits, and that is used to look into our hash table. Now everybody does hash tables for looking up these cryptographic hashes. And we take that, we map it into this table. If you were on Ceph or on Swift, you would be told, oh, you can go to server 1, server 2, and server 3 to get that object. And you just pick one of those. We do things a little differently. I'm sorry the cameras may not be able to see this very well, but we will have somewhere between 3 and, well, let's say 21 storage devices. It's not servers, it's the addresses of the storage devices that actually hold that information. And those storage devices, any one of those 21 devices can hold that information. So what we do is from this machine, we take the cryptographic hash, which I'll represent by that upside down triangle, and we multicast UDP that to all of the proxy servers that sit in front of storage devices. But the only ones we multicast it to are the members of this group. Only a maximum of 21 servers will see this message. And this number of servers is based on the total number of servers in your cluster. If you have, or excuse me, wrong statement. The total number of storage devices in your cluster, all right? And the algorithm we use is basically log base 10 of the number of storage devices times the replication count defaulting to 3. So it's only when you get up to on the order of hundreds of thousands of storage devices that you start getting into 21 servers that will be pestered with looking for the information. You're not going to be bothering 1,000 servers. You're only going to be bothering 21 servers to say, do you have this?
So Robert, you don't actually know which of those 21 servers has the data. You
have
just go
no clue. You go ask every
go out to
time.
these 21 and say, please, if you got this data, give it back.
Tell me who has it. Not only who has it, but you're going to negotiate. Because you're going to negotiate and say, tell me not only do you have it, but how fast can you deliver it? Because now you get an opportunity, instead of picking randomly one of 3 servers which may have random loads on them, you now by default get each of these server proxies representing these storage devices telling you, oh, I can name that tune in
5 milliseconds.
5 milliseconds, exactly. Or I can name it in 10 milliseconds. And now what you get is the fastest possible response. It takes us 2 round trips to complete the negotiation. Guess what? If you're holding open a TCP/IP socket, you've got 2 round trips going on all the time just to hold the sockets open. On top of that, with TCP/IP, if you have one device here that has to talk to 250,000 storage devices in your cluster, well, you've got a small problem. How do you hold open 250,000 TCP/IP sockets? You cannot. You would have to set up or tear down.
Storage devices, you could have multiple storage devices per node?
You can have multiple storage devices per server, yes. And each storage device will have its own address because, of course, a single NIC can have multiple IP addresses. So that's not a big deal, and that's how you sort it out. But with that 250,000 devices, the largest count I've seen from any server to talk to a number of sockets is 30,000 sockets. That's the largest I've ever seen, and that's in an extreme case. So to talk to 250,000 devices, UDP is exactly the right protocol to use because there's no setup, no teardown. The problem with UDP is it's called Unreliable Datagram Protocol. All right, so we had to put a layer on top of UDP called Replicast. Replicast makes sure that you actually get a response back. The great thing about this is when I ask these 21 servers who's got it and how fast can you provide it, I really don't care if some of those storage devices or servers have gone away. As long as I get answers from some of them, it just doesn't matter. This has a huge, huge implication for storage costs in the future. And the reason this has a huge implication is it means that storage manufacturers can make cheaper devices. If you look at what's happening under the covers on shingled magnetic recording, which is of course this technology that everybody's moving to even when they're doing key value stores, is that a shingled magnetic recording device every now and then has to go off and reorganize. It does reconsolidation of fragmented storage into sequential storage under the covers, so it goes away. And the SCSI folks have been working out these really nice protocols that says, I really need to go away, like I've got to go to the bathroom or something, to go and reorganize for a little bit, and then I'll come back when I'm done. With our implementation, yes, we can support doing that, but quite frankly, if you just get up and go and aren't there for a while and then come back, it works just fine because we'll just find it from somebody else that has it. And inherently, because of this negotiation process, when you get all these bids back, you get to pick the fastest one, which inherently means that you're getting the fastest possible delivery for the end user, which typically means that you're going to be distributing your workload to the least loaded servers. It could be that the storage device here with the 5 millisecond response could be a spinning disk. This one could be an SSD, but it had 10 millisecond response, not because the device was slow, but because the server was busy, because it had so many other requests in its queue. So now I go and I ask, I get a bid back, I take this bid, and I say, okay, you have the object for the biz plan, get the manifest. Everybody's got a manifest. You have to know what are the elements or the chunks that make up that object. So there's many chunks. Every time you want to get a chunk, now you'll have this server with the manifest, or who is the proxy server for the storage device, which was the manifest. Sorry, it takes a little time to say all that. It will then begin the process of getting that object and sending it back to the broker that's acting on the client behalf. And when it gets that, for each and every chunk, it has a list of chunks. For every chunk, it has a cryptographic hash, which might be beef dead is the first chunk that's in the manifest. And this server will now begin the process of broadcasting out who has beef dead, and when you've got it, tell me how fast you can deliver it, and then we'll work with this broker to schedule it getting back. Because now what's happening is that your retrieval time to get an object is not limited by the bandwidth on a server to get an object. It's limited by the inbound bandwidth on the client that's receiving it. This behavior is just like BitTorrent. Exactly. You're going to get these pieces being selected by the different chunks coming off different servers, all coming in, and they get scheduled. So and that's part of the Replicast protocol. I'm sorry.
So you are telling the manifest to send the chunks back to the broker.
Right. But it's doing more than that. It's Ginsu knives. What it does is it not only sends it back to the broker, but you may have a portal server here, which is a gateway off. Let's say this is SFO, and this is New York City. That portal server will get a copy of the information if it requests. To get a copy of the information, it simply has to subscribe to the multicast group of which these original storage devices were members. If I'm running instead a backup server, the same thing. Every time someone requests something, the backup server can say, gee, I'm a member of this backup, of this multicast group, and I see something coming by that I don't have a copy of. Then to get a copy, I simply make sure that I'm in the group that's going to receive a copy. The beauty of this is that by using UDP, unlike Swift, Ceph, or even HDFS, they all have to either push something 3 times, or they do a daisy chain where they push it, then the next guy pushes it, and the next guy pushes it, which induces a lot of latency. What we do instead is we take advantage of UDP, that when you push this into the network switches make the copies of the data and only route that data over the portion of the network that is tied to the target machines or the target devices that actually need to receive the data. And this means that it happens very efficiently. We're not doing multiple pushes. We're not loading down the network with multiple copies. The copies only get made in the network at the switches down the paths that actually need it. Yes?
So the broker is orchestrate all the stuff, and is it scale out? Does it run in the same nodes of the rest of the ring?
In fact, the broker is a service that runs potentially on every other server that's in the cluster ring. So you can have as many brokers as you like, and the reason that this works extremely well is if you're using a REST protocol to make these connections here, if for some reason this service fails, the server failed or the service itself failed, then your REST request will time out. You'll retry the REST. You'll re-access, I want a edge broker. And when you ask for an edge broker, your DNS round robin will find, oh, that one's not there. I'll give you a different one. And your request will be retried. And it's stateless because there's no state information stored anywhere here about where you were in the process of getting the file. Or getting the object.
Do you have a problem with eventual consistency or anything like that?
Yes. We are an eventually consistent object model. We are not transactionally consistent. Okay? I'm not going to try to be transactionally consistent. That is the #1 choice we had to make in going to this type of model.
So how can you split on different data centers? So
iSCSI device
globally.
Just hold on, one question at a time.
So you are using ODP now.
Yes.
How can you split the cluster in very far? And so most of the object storage system can split the cluster in two different, in two pieces of the same ring. Okay?
Yes.
So, and they can move it in a very far one from each other.
Yes.
Can you do the same with the?
We can, but we recommend that what you do is that you keep all of your transactional operations within a cluster, that your portal server here passes across the metadata about new objects to the foreign systems and vice versa. They pass them back. And that way, both systems know about all the data. Some of the data may be here, some of the data may be in New York. If you want to migrate the data, well, you may have a limitation on the size of your pipe between San Francisco and New York. It may not be able to hold a terabyte a day or 10 terabytes a day to send that information. So you put that information simultaneously on your backup server, and then your backup server uses this incredibly high bandwidth, but also incredibly high latency network called UPS. And you send the drives that hold the metadata and payload data by truck to New York, and the next day when it plugs in, it automatically correlates the metadata that it already has with the arrived data.
I am not understanding. So if I can have 3, 4, 5 copies of each single object in the ring. If I want 3 local copies and two
remote
copies.
You can do that. We don't recommend doing that. All right? There's another piece of it, because you do not want to wait for all 5 copies to complete to allow a user process to continue its operations. But there's another mechanism we have that could allow you to do that very neatly, and I'll get back to that after I address the iSCSI question. Sorry to stall you off on that.
Yeah, I mean, it's very unusual to see an iSCSI LUN device be eventually consistent.
Okay, so on the iSCSI LUN device, it is going through multiple versions of an object, right? That object,
or segments or chunks of an object, right?
Chunks of an object.
This could be, you know, a segment of blocks in a LUN or something like that.
Right.
Extent, as it were. Yeah.
So we provide a QEMU interface for it, and we also allow you to update the. What we've done is we have made a logical block is a chunk in our model, and there are multiple copies of that chunk. The LUN goes from version 1 to version 2 to version 3 every time there are updates that occur to the virtual drive, so that you keep updating that drive. And that drive is eventually consistent from the standpoint that any version is consistent. You just want to make sure that when you retrieve, that you retrieve the current version. So what happens is when we fetch this name through some magic always refers to the most current version known within the cluster that you're running. You have a potential challenge, as you do with any cluster, if the cluster gets split, that one side may know about one set of updates and another side knows about another set of updates. You will work with the cluster that you have at that time in making your updates.
So are you saying for iSCSI you've got enough magic in there to ensure that it's consistent, not eventually consistent?
That's right.
Using versioning.
Using the versioning.
And a version is any time a logical block.
Every time a logical block changes, then you've got a new manifest, because it's one thing I failed to mention at the very beginning. The underlying technology here is called cloud copy on write. It's one of the lessons we learned from ZFS. You don't change data in place. You write a new copy of data. If you rewrite data, you have a good chance to muck it up. And if you muck it up, you get all kinds of bit rot problems that can cause trouble. So there's always a new version of a new block or chunk. And that way you never have made an inconsistent model of the LUN. You just have to have the right version of the LUN at any given point in time.
And that version ties to a specific manifest, which is broadcast to the whole.
Which is made, well, it's not broadcast. It's if you request the name of the LUN, then you get the current version of the LUN to within the population that's known to the cluster at this time. Because, as I mentioned earlier, losing a single server or a single storage device is no big deal because of the way we behave. The worst case is if you have a network failure that splits you into two quorums.
Right.
If your quorums are, let's say, if the replication count's 3, if you're above about 35% of the cluster in your quorum, you've got a very good chance that you're going to get the current, most up-to-date version available somewhere in your quorum. Not a guarantee, but we do have some hints that say, gee, we're below 35%, maybe you should wait a while.
Now you mentioned the version part of this stuff that gets hashed into this first broadcast group, as it were, to say, give me the manifest?
So this is the one thing that we do, is that the name hash is the hash that's used to look up the manifest. The manifest is itself
chunk mask.
It's a chunk. The manifest is itself a chunk. We do not have a separate manifest store and a separate chunk store. We've unified all that into the same storage.
But inside that manifest is a list of other chunks that associated with this particular.
Yes.
So if I have a LUN, and I call a LUN like
yes.
Fox 24 or something like that. How do I know what version it's going to go? It's potentially have multiple manifests out there for Fox 24 at that point in time. Version 1, 10, 24, whatever.
So at the time that you fetch this manifest, there is, or excuse me, when you use this name, you use dead beef to look up the name. In the internal table on the key value drive, here's dead beef. And the value of dead beef is the chunk ID, the cryptographic hash ID of the chunk, which represents the most current manifest. The older manifests are provided in a list that you can access by their version number separately. Right?
So every hash value that you can compute here is going to have a different chunk ID? Is that, I mean, is
every name
collisions?
Well, this is why we went to 512-bit cryptographic hash.
All right, gotcha.
Yes, there can be chunk collisions, but current operating theory is that if you get a chunk collision, the probability of that happening is about the same as the sun will be nova tomorrow. All right? We have built into our protocol and into our on-storage format the ability to extend those hashes.
In the cluster, I'll call it, can get a request for this LUN at any instant in time.
Yes.
And it's going to do this hash on its own version of this hash table, right? Not like the hash table is it mirrored? Is it distributed?
The flex hash table, and we call it the flex hash, is copied on every server. The flex hash only changes in terms of the flex hash table when new storage devices enter or leave the cluster. That's the only time you update the flex hash table, because all it does is map a hash to a row number, which gives you the set of devices. Within that set of 3 to 21 devices, They have to maintain a copy of the cryptographic hashes that they have mapped for specific names within those storage devices. Storage devices within the same hash may have different objects. All right? So that those objects can be in different subsets of the multicast group. So I have one little prop right here. I'm going to just try and get this stuck to my leg. And let's see if we can get that. It's coming apart.
Thing, yeah.
And I'm running out of time. All right. So let me just talk about a little bit of market speak versus engineering speak. So the market question might be, how do we handle deduplication? How do we handle load balancing, which I haven't had time to talk to because we're running out of time. What drive models? I've already mentioned we handle key value. Do we do anything centralized? The answer is no. We'll talk about why. And how do we do capacity management? So let me just, from a marketing standpoint, it's typically referred to as inline deduplication. Engineers talk about it differently. We'll get back to that. Load balancing is dynamic. Okay, so that you saw how we do the bidding process, the negotiation process to get new load balancing. Key value drive model, there is no central bottleneck anywhere in our model, and we can do balancing of capacity across the drives. Our deduplication is real-time and distributed. It's real-time and distributed from the standpoint that the deduplication is being done in parallel by multiple storage devices and their proxies at the same time. There's no central store that's doing the deduplication because we've sharded the cryptographic hash space into tiny pieces that are manageable for those storage devices. Everything's managed at the edge. There's no central management in this model anywhere. Every service asks for items and asks for them from a group of items which are in a multicast group. Key value, the real important thing about key value is its delayed binding. We have lived for the last 125 years with the block model of storage. Now that sounds a little crazy because there haven't been disk drives for that long. But the block model storage comes from the Hollerith card because a block was a collection of unit records. If you pick up any book on file systems, the very first thing they talk about is the unit record. And then a block is composed of multiple unit records. All of that goes back to the Hollerith card, which was first used in the 1890 census for the US Census Bureau. So we're living with 125-year-old block technology. It's time to get rid of it. All right? By doing key value, we have not bound storage to a location. We don't know where the storage is. We don't want to know where it is. We have networks that provide the answers very, very quickly. This also allows us to have a global, decentralized namespace because the namespace is sharded into very tiny pieces which are manageable by small storage devices. These storage servers could be as simple as an ARM CPU with one drive attached. Oh gee, is that a kinetic drive or is that an HGST Ethernet attached drive that has an ARM CPU and actually a SAS drive attached to it? Sure, we could run into that. We could run on that with most of our code. And the load balancing, or the balancing act that we do, we can balance by capacity, by failure domains, and we can balance by performance domains so that when you're putting an object across a set of storage devices in that multicast group, you can make sure that the different replication copies are in different failure domains, which might include different cities, or different performance domains, which might include flash, RAM disk, or spinning disk, or different capacity domains. If you see that one disk drive is filling up, then you can migrate storage off that disk drive as a background process to level out the storage across the system on an automatic background basis, on a continuous basis. There's a whole lot more to this. There's papers coming out on it over the next 3-4 months, and love to spend more time when we can, but I think I'm out of time.
Alas.